So now we're going to close out this section on the chain rule by doing an example of a related rates problem. You might remember these from probably Calc 1. Right? So what's the setup here? Well, here we have a box containing an incompressible fluid. What that means is no matter how much you try and smash up the box, the fluid always takes up the same amount of volume. All right? So what we're going to do here is we're going to keep the height fixed at a certain amount, and then we're going to squeeze the width. Right? And then what we're going to ask is, well, how fast is the length of the box changing? Because if you think, if the volume has to remain constant, that's what incompressible means. If we squeeze one direction, the other one should grow. That hopefully makes sense intuitively here. So how do we do such a problem? Well, first off, what's the volume of a box? Well, the volume is width, length, height. Or length, width, height, I don't know, whichever way you want to write it. Right? So what's the setup here? Well, since we're altering the width and length, really all of these guys depend on time. All right? So we can draw a dependency tree. V depends on width, length, height. The width is changing with respect to time. The length is also changing with respect to time. And the height, well, actually, we're holding the height constant. So it actually won't depend on anything. We could put a t here, but since h doesn't actually depend on t because we're holding it constant, that derivative would always be 0. So really, this is all we need. So what are we asking in the question? We're asking how fast is the length changing when the width is 3 inches? So what we're trying to ask is, what is dl dt when the width is 3 inches? Right, so we actually know all the other variables as well. All right, so let's begin by trying to figure out what is dl dt. Well, so we can take dv dt, and using the chain rule, we can get our hands on dl dt. So dv dt, or if you like partials, but it doesn't matter in this case. Right, dv dt, well, we're going to have dv dw. What is that? That's just LH. And then dw dt. Sorry. dw dt. Okay. Plus dv dl. dv dl is wh times dl dt. Right? And then, well, there's no t here. Right? So we have that. We also know what dv dt is. Right? So incompressible means that this is 0. It's not really a contrast in colors there, is it? Let's redo this with orange. Right? So because it's incompressible, we know the volume never changes, and if the volume never changes as a whole, then dv dt has to be 0. All right, so now we need to start plugging these guys in. Right? The thing we're looking for is this. So what do we know? Well, we know that 0, right, so the length is, well, we don't know the length yet. So L. The height is always 7. Right? And the dw dt, well, we're saying we're squeezing the width of the box so that it decreases at a rate of -1 inch, or at 1 inch per minute. So dw dt is -1. Right? All right, and then plus wh So we want when the width is 3 inches. Again, the height is always 7. And then we're looking for this. So we need to figure out L. Well, remember, the volume, which is width, length, height, is always 42. Okay? So we don't know L, but we know W is 3, and we know H is 7. So that's going to tell us that L is 2. Right? So we get here 0. So 2 times 7 times negative 1 is negative 14. Okay? Plus 21 dl dt. Now we just have to solve for dl dt. Well, what does that mean? That means we move this negative 14 to the other side, it becomes a 14, and then we divide by 21. So dl dt is 14 over 21, and this is going to be inch per minute. And of course that simplifies to 2/3 inches per minute. Okay? So hopefully that made sense and was pretty straightforward. And again, just as in the Calc 1 problems, the thing is to identify the information in the example, in the statement. Okay? Well, that's it for the chain rule. Hopefully everything here makes sense, and happy practicing.